This is 48D video 1, and we're going to talk about vectors. We'll begin by talking about a system of coordinates, the ways we can measure space, and then we'll talk about vectors and scalars. We'll then look at three different ways of dealing with vectors. There's vector diagrams, there's vector coordinates, and then there's a very interesting system called IJK unit vectors. We'll talk about those three methods of dealing with vectors. Coordinate systems. Well, coordinate system are a frame of reference. A coordinate system is used to specify locations in space. Could be in 2 dimensions, different points on a page. In 3 dimensions, you could imagine it as different points within a room. Coordinate system must consist of, well, you need a fixed reference point called the origin. On the number line, we call it the number 0. On a graph, it would be, for example, the origin, the 0, 0, 0 in x, 0 in y point. And in a 3-dimensional space, there'd be also a similar origin. We need a set of specific axes or directions, and then we need instructions on how to label a point in space relative to the origin and the axes. There are 2 dominant coordinate systems. There's what's called a Cartesian coordinate system, which basically consists of orthogonal, that means at 90 degrees, linear axes. So we have an x-axis, we have a y-axis, and in 3 dimensions we'd also have a z-axis. And the beginning point, the origin, is at the 0 point of all those axes, and then we need a set of rules for how to name things. In 2 dimensions, the pattern is that we say how far along the x-axis are we, and then we'll put that down as the first coordinate, and then we'll say how far are we along the y-axis, and we'll put that down as the second coordinate. And if we had a third coordinate, if we were dealing in 3-dimensional space, we'd have x, we'd have y, and then we'd have z. These axes are at 90 degrees to each other, so they are orthogonal and they are independent. If you can move on the x and it will not affect your position on the y, you can move on the y, it will not affect your position on the z. They're independent. Another way of dividing up space, and here we're going to look in 2 dimensions only, is the plane polar coordinate system. And for the plane polar coordinate system, we take an x-axis going from the origin outwards, and then we define our point of interest by saying how far is it away from the origin, and then what is the angle to the x-axis going in a counterclockwise direction. And we'd represent it by r, meaning the distance from the origin to the point of interest, and theta, meaning the angles from the x-axis. We spend the vast majority of our time dealing with the Cartesian coordinate system, though you will, especially if you continue, you will see the plane polar coordinate system coming up, especially when you're dealing with circular systems. Just to digress briefly, if I wanted to talk about the points of a circle, every point on this circumference has a different value of x and a different value of y, and so if I saw a table of data points, I might not even recognize it was a circular graph. But if I looked at this on a plane polar coordinate system, then every point on this circumference has the same value of r and a steadily increasing value of theta, and so it's easy to identify. You use the best coordinate system for what you're going to work with, and most of the time we deal with the Cartesian coordinate system. Here's a system, a point represented by 3, 4, so let's draw it. It's 3 steps on the x-axis and then 4 steps on the y-axis. So the point is here. A point represented by 3, 4 on the Cartesian coordinate system. Express this in the polar coordinate system. So what we need to do is we need to find out the r and the theta. We know the x and we know the y, but we need to know the r and the theta. Well, a little bit of thought will tell us that r squared is equal to x squared plus y squared, because it's a right triangle. This is a 90-degree triangle, and so we have our r value, our y value, and our x value, and so we can see that r squared is equal to 3 squared plus 4 squared, which equals 9 plus 16, which equals 25, and so r is equal to the square root of 25, which equals plus or minus 5, and in this case we're talking about a length, so it would be 5 meters long. And actually this is such a common triangle, the 3, 4, 5 triangle, that is often used in calculations because, you know, with practice you can just spot that the hypotenuse, the length of the longest line, would be 5. What about the angle? Well, the angle, we know that tan of an angle is equal to the opposite over the adjacent, and as I look at my diagram, the opposite is going to be 4 and the adjacent is going to be 3. Let's be clear, the angle is down here in the corner, and so I have 1.33, so theta is equal to tan to the minus 1 of 1.33. And so I get my calculator and I say, oh, it's second tangent 1.33, and I get an answer of 0.92 radians. And sometimes I'll get an angle of 53.1 degrees. And yeah, it depends on the mode of my calculator. Both answers are correct, but if I click my calculator into the radian mode, which we actually do quite often in different parts of physics, then I'll express the angle in radians, and if I have my calculator clicked into the degree mode, I'll get my answer in terms of degrees. So don't be put off by that. It's just the way it is. You've got to check your mode. Every time you're doing anything to do with angles, check the mode of your calculator. Now let's divide the world up into vectors and scalars. A parameter is either a vector or a scalar, and you should know which it is. So if I later on talk to you about momentum, we'll be clear to decide what it is. Is it a vector or a scalar? If we're going to later on talk about impulse, which is it? It's important that you find out. And a scalar has a magnitude but not a direction. So a very typical example is mass. Mass would be a scalar because you don't say it's 6 kilograms in that direction. It's just 6 kilograms. So when something doesn't have a direction within a room, then it's a scalar. A vector is something which has both magnitude and direction. So for example, weight has a definite direction. It's a force. If I go from point A to point B in a room, displacement has a magnitude and a direction, and even something like a velocity points in a certain direction, and even something like an acceleration points in a direction. So the examples that we commonly use of vectors are displacement, velocity, and acceleration. Which is the vector in the following list? Well, speed is not. Speed has a magnitude but no direction. Average velocity, well, velocity certainly is, and making it an average makes no difference. It's still got a magnitude and a direction. So average velocity is a vector. Let's check the last one, time. Time is just a scalar, it's just a value that keeps changing. We don't say 5 seconds pointing towards the refrigerator. It makes no sense. So the answer to that one would be B. If we want to deal with vectors, then often we'll want to add vectors together. There's 3 ways we can envisage adding vectors together. The most direct way is to add the vectors together using a vector diagram. In 2 dimensions we simply draw vector A and then we draw vector B. The process of addition is drawing the tail of vector B on the head of vector A. So a vector consists of a length, a line with an arrowhead because it points in a given direction, and the process of adding vectors is drawing the tail of vector B on the head of vector A. If you like, we complete vector 1, and then addition is then adding vector 2. We go from the point of vector 1's end and start vector 2, the second one. And the resultant is a replacement. And so it begins at the beginning, so the tail of the resultant should start at the tail of the first vector, and it ends at the end. And so the head of the resultant must match the position of the head of the last vector. Now we might have more than 2 vectors, and the vectors might be abstract. We might not be adding displacements, which seem reasonably straightforward. We could be adding accelerations, getting a quite abstract process here. The limit of the vector diagrams is that there's always a little bit uncertainty about how you draw things, and so reasonable people end up with slightly different answers at the end of a vector diagram process. So it lacks precision. We need to bring some math in, and so the most typical way that's done is that the original vector, in this case vector A, can be divided into 2 components, the x component and the y component. From a vectorial point of view, vector A in the x direction plus vector component AY in the y direction do the same job as vector A. Now for us, going on a journey, if we had to go all the way to the east until we were south of the city we wanted to visit, and then we had to go all the way north, it would be clearly a longer journey. But we're not dealing with that. Vectorially, it makes no difference. Effort does not matter. The fact of the matter is that if I did vector A as the original vector, or I did the horizontal component of vector A and then I did the vertical component of vector A, the end result would be the same. So these are equivalent. And for vector B, I could divide vector B up into 2 components. So I could have an x component of vector B and a y component of vector B. And what I end up with is an x component of my answer, the resultant, and a y component of my answer, the resultant. And if I put those 2 together, I get the same resultant I would have got from the vector diagram. The difference is that I can use components, I can use trigonometry to do this exercise, and I can have more precision. Vector components work very well in 2 dimensions, but they get cumbersome in 3 dimensions. And so people introduced IJK notation. Basically, the idea is rather than saying here's a vector, oh by the way it's in the x direction, what we say is, oh, here's a vector, it's so many units long in the x direction. The I vector symbolizes, represents 1 unit's length in the x direction. The j vector is a unit vector. It symbolizes 1 unit step in the y direction. I always found for 2 dimensions it was just as easy to do things in components as it was to do things in IJK notation. But for 3 dimensions, IJK simplifies the way you write things down, and so for that reason it's very beneficial. Let's do some examples. Vector addition diagram. Let's look at this. So for a vector addition diagram, we draw vectors in sequence, head to tail, with the appropriate magnitude and direction. The resultant vector extends from the tail of the first to the head of the last. The order sequence does not matter. So now you will be doing this with a ruler. I'm going to do it freehand, but I'll show you the example. Use a diagram to find the resultant vector of these force vectors. So they're force vectors. Let's say this is A, and let's say this is vector B, and I can add them up in either direction. So what I do is I draw A. My drawing has the same length as the original vector and the same direction. This is vector A. Put a little arrow on top to tell everybody I'm dealing with a vector. Now I want to add vector B, and so I go to the tail, to the head of vector A, and I put my tail of vector B, and I draw a vector just as long as vector B in the same direction, and this is my vector B, and by drawing them head to tail, that's constructed for me my vector diagram, and I can draw in my resultant vector, and there's my resultant vector. It starts at the beginning of the beginning and it ends at the end of the end. And the thing I got to warn you about is that because vectors have arrowheads, you must be careful to show the arrowheads. Just drawing a series of lines does not tell the viewer where the vector R, the resultant, goes from the bottom left to the top right or from the top right to the bottom left. So you must put your arrowheads in here. But there's a vector diagram. It's incredibly useful. It's telling me that the resultant force, the result of having these 2 forces acting on an object, would be a force which goes in this direction and would have a size given by the arrow's length. It's really a very impressive system. Supposing, because of some mathematical reason, I want to subtract vectors. How do I do that? Well, the trick is I recognize that vector A minus vector B, remember the arrowheads on top mean it's a vector, is the same as vector A, which is a vector, minus plus vector minus B. So I'm changing the operator from a subtraction to an addition, but I'm adding on the negative of vector B, the opposite of vector B. If this is vector B, then the opposite of vector B is this. This is minus vector B. If this is vector C, then this is minus vector C. So in this diagram I have a vector A, and if I want to add vector B, I put the tail of vector B on the head of vector A, and I simply draw my resultant. But if I have a vector A and I want to subtract vector B, I simply add on vector minus B, and so it goes in the opposite direction and I end up with a completely different answer. It's a completely different answer. Subtracting vectors diagrammatically, we want to determine the value of vector A minus vector B. We simply add vector A to the vector minus B. So vector A minus vector B is the same as vector A plus vector minus B. And then the next one we might want to do is multiply a vector by a scalar, by just a numerical multiplication factor. If we want to multiply a vector by a scalar, the result is a vector which is in the same direction as the original vector, but has a magnitude scaled by the scalar value. So 3a gives a vector which is in the same direction as vector A, but 3 times its length. So if this is vector A, vector 3a has the same direction, but it has 3 times the length. There is also vector multiplication. That's a vector multiplied by a vector, and we'll get to that later. We do it, but we'll get to that later. So let's try this. Let's bring some of this together. So I have a command, draw vector 2b and subtract vector A. So there's vector B, there's one of them, and here's vector B, there's the second one. And then rather than adding vector A, I'm going to add vector minus A. Let's label these. This is B, this is B, and this is minus A. It's minus because it goes in the opposite direction to A. A goes in that direction, minus A goes in the opposite direction. So the resultant starts at the beginning of the beginning and ends at the end of the end, and so my resultant looks like that. My resultant equals that. They're really nice. Once you get the hang of them, they're really nice, and they encourage you to think visually, which is always a good thing. So let's have a look at this question. Using a diagram, determine the resultant vector of A minus 2b. So let's draw A, and then rather than adding on B, we're going to add on minus B. So there's one minus B added on, and here's another minus B added on. So this is vector A, and this is vector B, and here's the second vector B. And then again, we put our resultant in. Our resultant starts at the beginning of the beginning, and it ends at the end of the end. And because these are vectors, you must be careful to make sure you clearly show the arrowheads. No arrowhead, it's not a vector. So watch out for that.